All right, great. So it's our great honor to have Po-Ling speaking about statistical estimation rates. And in order to not delay the talk any further, I'll let Po-Ling take it away.
Right, thanks very much. So thank you to the organizers for inviting me to give this presentation. I really wish I could be there in person, but I'm glad that I have the opportunity to present virtually. So I decided that since this is a tutorial talk, or bootcamp talk rather, I would give the talk via writing on an iPad. It's a bit difficult because I don't actually have any expressions to go off of to know whether I'm going too fast or too slow. But I'll try to go at a reasonable pace, and please do feel free to stop me if you have questions about anything. So the topic is lower bounds on statistical estimation rates under various constraints. And we are going to be covering 4 different topics. So the first one is just the basics of information theoretic bounds. And then the second one is lower bounds under the constraint of robustness. Then the third topic will be lower bounds under the constraint of differential privacy. And then the fourth one will be constraints of computation. And roughly speaking, we'll have 1 lecture for each, although differential privacy will probably be slightly longer and computation will be slightly shorter. And that's because I think many of the other bootcamp speakers are talking about computation. And some constraints which are not covered are communication constraints, which are also studied, and other constraints like memory or storage constraints. So we will focus here on lower bounds. So we will focus on establishing lower bounds and only mention algorithms that achieve the same upper bounds. Okay, so as you'll see, the methods that we use for proving lower bounds will all be information theoretic. We want to know what's the best performance we can hope for from any estimator. We'll also want to know in practice whether or not we can achieve these bounds. But oftentimes the proofs for proving upper bounds are quite different from the proofs for proving lower bounds. So I'll just tell you in each of these cases what the algorithms would be without proving anything. Okay, so let's dig into topic 1. So topic 1 is basic lower bound techniques. Okay, so what we want to do, well, here's a reference. So I'll give you a reference for each one of the lectures. We'll go off of material in the textbook by Wainwright, High Dimensional Statistics. From 2019. Oh, another thing I wanted to say is that I will be doing quite a few computations and derivations and proofs. And the reason is that I sort of want to make the process of proving lower bounds a little bit less mysterious. So I would like to include details so you can kind of see how these things work. But I won't have time to go through all the details, so I'll skip some small technical statements that are plausibly true and you can look up or try to prove by yourself later. So we want to characterize the minimax risk which is defined by infimum over estimators theta, supremum over distributions in some set script P, expectation where the data comes from P of some loss function applied to an estimator, which is applied to the data, and some parameter of the unknown distribution. And here, P is a class of data generating distributions. And the expectation is taken with respect to a particular distribution, P in script P. And the parameter of interest is some functional theta of P. There's a particular case that we will focus on, which is when we have a parametric family. So a special case, and I think this will be the case for all of the examples that we cover in all of our lectures. So script P is a parametric family. So P theta, and we're going to say P theta to the end because we're going to assume we have IID observations. All right, so P theta, P is a parametric family.
Po-Ling, do you hear us if we ask a question just like this?
Sorry, go ahead. What's your question?
Yeah, this is to the trigger link. I just have, it's a little small when it comes out on this portrait. Would you be able to switch to landscape by any chance?
I can try that and see what happens. Let's see. You'll see that I don't use iPads very often.
Down on the right side at the top, and then it should be like
Here we go. Okay, and I don't want that lock to be on. There, is that better?
Yeah, thank
Much
you.
better.
Okay. Great. All right, but now I might have to write giant too. Okay, so a special case is where script P is a parametric family. And we have IID observations. So X is IID from P sub theta. Then the minimax risk. Can also be written as an infimum over theta hat, supremum over parameters theta in capital theta. Expectation, where X is the data, is a data set of IID points, which we're going to denote by X distributed as P theta to the n, the product distribution. And now it's the loss between theta hat applied to the data and the true parameter theta. Okay, so I think in all of the examples that we're going to go through, we'll be looking at a parametric family. But in the first lecture, at least, we're going to derive these results in more generality. So we will suppose throughout that L has a special form. So the loss function that we're using is of the form phi composed with rho, where phi is an increasing function. And rho is a semi-metric, which means that it has 3 properties. So it satisfies the triangle inequality. It satisfies symmetry. So rho of uv is equal to rho of vu, and also rho of vv is equal to 0. Okay, the reason why we do this in more generality is that, for instance, as an example, we might want rho is equal to some sort of a norm, which satisfies the triangle inequality, and then phi is equal to the square. Because, for instance, maybe we want to measure these risks in terms of the squared L2 norm. And we will need to apply a triangle inequality, but we can't do it directly on L. Okay, so the main tool that we're going to focus on is Fano's inequality. So in this part, I'll both remind you what Fano's inequality is and give you the general technique for proving lower bounds. So the idea is to transform the estimation problem into a decoding problem. And the goal is to infer the correct message from a discrete set of messages corresponding to a collection of distributions to, well, let's say it to a subset of the whole class of distributions. And the estimation problem is at least as hard as the decoding problem. If the distributions are well separated. So this is all a little bit abstract, so let me tell you precisely what I mean. Okay, so consider a set P1, P2, PM, which is a subset of script P, such that, now here's the well-separated part, we need rho of theta of Pi, theta of Pj to be greater than or equal to 2 delta for all I not equal to j. So remember the rho semi-metric operates on the theta space. Now let psi of x, a particular, well, I guess it's not exactly an estimator, but it gives you an index. So let psi of x be the decision rule. Psi of x equals arg min over all indices j of rho of theta of pj, theta hat of x. Okay, so what this means is that we have these well-separated distributions, at least in the theta space. So you can think about theta of p1, theta of p2, etc. Then theta hat of x lands somewhere. Let's say it lands here. Okay, that's the particular output of an algorithm. And then what this, what psi does is it maps it to the closest one. So in this case, gets mapped there, and psi would just be the index 1. And we'll say where ties are broken arbitrarily. Okay, so now we write the following. So then expectation, where x comes from pi of, I guess it's pi to the n. Oh, sorry, no, it's not pi to the n. So this is the general situation where pi is a distribution in, let's say, the whole product space. We have L of theta hat of x and theta of pi. And this is going to be greater than or equal to phi of delta times probability. So here we're applying Markov's inequality. Probability that L of theta hat of x, theta of pi is bigger than or equal to phi of delta. And this is equal to phi of delta times, now we use the fact that, that L is equal to phi composed with rho, and phi is an increasing function. So we just get rid of the phi. X is distributed as pi, rho of theta hat of x, theta of pi greater than or equal to delta. And now this actually is greater than or equal to phi of delta times the error probability. Probability that when x is distributed as pi, psi of x is not equal to I. Okay. So why is this last statement true? Well, if you think about it, let's say star comes from the containment that the event that rho of theta hat of x, theta of pi is less than delta is contained in psi of x is equal to I. Okay, so so if this event is true, then certainly the probability that the right-hand side is not true is less than or equal to the probability that the left-hand side is not true. That's where we're getting this. And then why is this containment true? Well, if phi of x is closer than delta to the actual distribution, then it will get mapped to the correct thing. And this is because we have assumed that that all of the distributions are 2 delta separated, right? Okay, good. So now what do we do with this? Well, our risk had to do with a supremum over all distributions P of this sort of loss. So of course we can lower bound the supremum by an average of several distributions. So now we say that supremum over P in script P of expectation x distributed as P of L of theta hat of x, theta of P is going to be bigger than or equal to 1 over m, sum I goes from 1 to m, expectation under x distributed as pi of L of theta hat of x, theta of pi. All right, and now we have, well, this this statement out here gives us a lower bound that we can just plug in. So this is bigger than or equal to phi of delta over m times the sum I goes from 1 to m of probability x distributed as pi psi of x is not equal to I. Okay, so we have this lower bound on the risk. And now here's where we use Fano's inequality from information theory. So recall Fano's inequality. And that says that for any estimator, y hat of y, such that y to x to y hat forms a Markov chain, we have probability y hat is not equal to y is lower bounded by h of y given x minus 1 over log base 2 of script y, where y is the range of y. Okay, so this is like the probability of error, if you will, of any estimator. So here you can think about trying to estimate what y is, you get an output y hat, and this lower bounds the probability of error of any estimator. Okay, so we're going to apply this Fano's inequality to get a handle on these guys. So now let y be distributed uniformly on the index set 1 up to m, and let x be distributed according to p sub y. Remember, p sub I are all the distributions in this collection that we're considering. So then applying the lemma with y hat equals psi of x, then gives 1 over m sum I goes from 1 to m of probability x distributed as pi psi of x not equal to I. So this is the quantity that we care about from up here. And this is going to be equal, oops, my eraser. So this is equal to the probability that y hat is not equal to y. And by Fano's inequality, this is bigger than or equal to h of y given x minus 1 over log base 2 of m, since our set had size m. And we can rewrite this as log base 2 of m minus the mutual information between x and y minus 1 over log 2 of m. And why is this true? Well, this is just because of the conditional entropy. Since I of xy, or I of yx, is equal to h of y minus h of y given x, and h of y is equal to log 2 sub m, since y is uniform. Okay, so altogether, our main result is that infimum over theta hat, supremum over p in script p, expectation x distributed as p, L of theta hat x, theta of p, is going to be bigger than or equal to. So actually there was an extra, oh, screen sharing ended. Let's fix this. Okay, so where were we? Yeah, I guess I was scrolling up to say that there was an extra factor of phi of delta, and then whatever we get from, well, let me just scroll back up. So what we wanted was, we have just lower bounded this stuff. So we have an extra factor of phi of delta, and putting it all together, we have 1 minus I of yx plus 1 over log base 2 of them. Okay, so this is the lower bound that comes from Fano's inequality. And now, so the main point is that to apply this, the inequality in practice, we need to, let's say, A, construct an appropriate set, an appropriate 2 delta separated set in the row metric, and B, upper bound the quantity I of yx. So I'll say that at least in most of the applications, what you do is you try to lower bound this whole quantity here by 1/2, so that the rate that falls out is of the order of phi of delta. So if you want to lower bound this stuff by 1/2, then that means that you want to upper bound I of yx. Okay. So let's now talk very briefly about how you usually upper bound I of yx. So the next subtopic is bounds on mutual information. All right, and so what you do is, well, for now, so let's write P bar to be equal to the mixture distribution 1/m, sum j goes from 1 to m, pj. So let this be the mixture distribution. Then we can check that. I of yx is equal to 1/m, sum I goes from 1 to m of the KL divergence between pi and p bar. And this, it turns out, is upper bounded by 1/m, sum I goes from 1 to m, 1/m, sum j goes from 1 to m of the KL divergence between pi and pj. And this last inequality comes from the convexity of the KL divergence in the second argument. Okay, so therefore, to upper bound I of yx, it suffices to obtain bounds on pairwise KL divergences. Now, of course, this bound could be loose, and there are definitely cases in which this is not what you want to do. But then there are also cases when it's easy to construct a set and also and verify that the parameters are 2 delta separated, and also verify that the KL divergences are pairwise bounded by something. Okay, and this method is known as the local packing approach. Okay, so to make things a little bit less abstract, now we're going to run through a few examples. We're going to run through 3 examples, and these examples, in addition to helping you understand how you would use these results, actually these are examples that we're going to be returning to when we add on different constraints later on. So the 3 examples are normal mean estimation, normal covariance estimation, and high dimensional regression. Okay. And as I said, I will go through some of the parts in more detail than others. So let's first talk about normal mean estimation. Okay, so what we have is, so this is a parametric problem. We have xi, which are coming iid from a distribution, normal, theta, sigma squared, I sub p, so p-dimensional normal distribution. And the goal is to estimate theta, which is living in RP, okay? So we will show using this method that infimum over theta hat, supremum over theta in RP, expectation where we have IID data coming from P theta of theta hat minus theta, 2 norm squared, is of the order lower bounded by sigma squared P over N. Okay, and as I said, I'm not going to talk about upper bounds, but a matching upper bound can be obtained just using the empirical mean. Okay, so another way of thinking about this is, maybe you have an estimation problem, you have an estimator that you think should be a good one. You get an upper bound, perhaps by deriving some concentration inequalities, and you want to know whether or not there's some estimator that could do better. And what this is saying is that, in fact, there isn't any estimator that could do better. Okay, so how do we achieve the lower bound? So we will use Fano's method with rho equal to the L2 norm and phi of t equal to t squared. Okay, so that's how we get the squared L2 norm for our loss. Now, let script v be 1/2 packing of the unit L2 ball. So we'll use this notation again later. So let's call it B2 of 1 in the L2 norm. So what do I mean by 1/2 packing? Well, this is the language of metric entropy. So this means that I have my ball of radius 1 in L2 norm, and I want to place points in it so that pairwise distances between any two of them is at least 1/2. Okay. So now by standard results, such a set of cardinality script v bigger than 2 to the p exists. Okay. So now we need to, well, this is just a packing of the unit ball. Of course, our whole parameter space is all of our p, so we can do different things with this. What we're going to do is rescale this packing to obtain the parameters theta that pack our space. The other thing is, of course, we want it to be 2 delta separated. Here it's 1/2 separated, so we need to get the delta in there somewhere. Okay, so now for each v in script v, we define theta sub v equal 4 delta v, where delta will be determined later. Okay, so here's where we're going to get our 2 delta separated part. And actually, this will hold for any delta, but then the whole game is to set delta later and a bound will fall out. Okay, so now let's check that this is 2 delta separated. So for v not equal to v prime, we can verify. So we're looking at these parameters, and we want these parameters to be at least 2 delta apart. So remember that our metric was the L2 metric, so now we're looking at separation in terms of L2 norm. And this is exactly equal to 4 delta times v minus v prime. And this is then going to be at least 4 delta times 1/2, since this is 1/2 packing. Okay, good. So we scaled everything correctly, and we have 2 delta separation. And now the other thing that we need to do is we need to get an upper bound on the KL divergence between pairs. So we look at PV and PV prime, right? Because by Fano's inequality, we wanted an upper bound on pairs. And you can calculate this. So remember, what is PV? Well, P is a Gaussian distribution, right? It's a Gaussian distribution up here with mean, whatever we get from V, and variance sigma squared times the identity. Now, the parameter is 4 delta times V. So really, we have a KL divergence between 2 normal distributions where the means are 4 delta V and 4 delta V prime, and the covariance matrices of both are sigma squared times I. So you can check that this is equal to 16 delta squared over 2 sigma squared times v minus v prime. 2 norm squared less than or equal to 32 squared over delta squared. Okay. And right. Okay, so oh yeah, one thing I wanted to note was that we have this formula for the KL divergence between two normal distributions, mu1 sigma 1 and mu2 sigma 2. So I'm just writing this out just to remind you. We'll use this this expression for several different KL divergence problems in these tutorials. This is the log of the determinant of sigma 2 over sigma 1 minus p plus trace of sigma 2 inverse sigma 1 plus mu1 minus mu2 transpose sigma 2 inverse times mu1 minus mu2. Okay, so to get this equality here, we're really just plugging it into this more general formula. Okay, so what's the point? Well, one thing to notice is that actually, so therefore, I of yx is bounded by 32. Well, okay, I should say I of yx is actually bounded by dkl of pvn prime. Okay, so if we go back, maybe you already realized this, but we go back to our bound on the mutual information, right? We want our mutual, we said that if the pairwise KL divergences are bounded by something, mutual information is bounded by that thing. But now we need to remember that in this more abstract statement of, well, in our derivation of Fano's inequality, we were dealing with these PIs as being the n-fold product distributions. And down here, when I've computed this KL divergence, this was just as if we had one sample from a Gaussian distribution. So really, we need to be looking at the n-fold product distributions. Well, we know that the KL divergence tensorizes, so this is n times dkl of pv prime. So our bound tells us that this is bounded by 32n delta squared over sigma squared. Okay, so now we have all the ingredients we need. So then Fano's inequality implies the lower bound of delta squared. So in Fano's inequality, we have phi of delta. Remember that phi is the squared function. And then 1 minus the KL divergence upper bound, 32n delta squared over sigma squared. And there was a plus 1. And then we divide by the log of m, which is going to be equal to p. Okay, so let me just scroll up again to remind you. Well, Fano's bound, we have a log base 2 of m. M is the size of the cardinality of the set. And I said that there exists packing which has size at least 2 to the m. 2 to the p. So log base 2 of that is just p. Okay, so now what do we do with this? Well, as I said, the game is to say, well, how should I choose delta squared so that this is lower bounded by 1/2, right? So, so if you want to set the second quantity equal to 1/2, then you can manipulate things, and you'll see that what you should do is you should take delta squared to be on the order of sigma squared p over n. Okay, so we just repeat that. To make this guy order of 1/2, you can rearrange things, so delta squared should be this order. And then that says that we can ignore the second term, and our rate is really just delta squared. So this implies that the minimax risk is omega of delta squared p over n, which is what I claimed up above. All right, so that's example 1. And now let me do example 2. So, and you'll see that there's some similarities here, but let's just go right ahead and do it. So this is example 2, which is covariance matrix estimation. So you'll see that here constructing the packing set is a little bit different. So now the problem is that we suppose that we have xi, which is distributed iid as normal 0 sigma, and the goal is to estimate the covariance matrix sigma r to the p by p from the parameter space. We're going to define theta to be equal to all matrices sigma, which are PSD. So let's write it like this. And also the spectral norm is bounded by lambda. So here I mean, this is the PSD cone, and this here is the spectral norm. Okay. And we will show the bound infimum over estimators sigma hat, supremum over estimators sigma hat in our space theta, expectation x distributed as p sigma, and again we have an n-fold set of samples. Sigma hat minus sigma, 2 norms squared, is equal to omega of lambda squared p over n. Okay, so lambda, remember, is our bound on the spectral norm over the class. And an upper bound, so a matching upper bound can be obtained using the sample covariance matrix. Again, using concentration inequalities. Okay, so how are we going to establish this lower bound? Well, of course, we'll use Fano's inequality. So we'll apply Fano's inequality with rho is equal to the spectral norm of matrices, and phi of t is equal to t squared. So again, we have squared spectral norms, so we're going to do it like this. Now we need to define the set that we're going to use. So here I'm going to skip a bunch of details and just give you the main ideas of the construction. So for r greater than 0, define the set case of r, k of r is equal to lambda over 2 I plus bf. Let me just write out the expression and I'll tell you what these notations mean. Intersect b2 of 1/2, intersect sp. So this is bf is the Frobenius norm ball. And then b2 is, of course, the spectral norm ball around 0. Okay, and this sum here is the Minkowski sum. Which I guess just means that what we're doing is we're taking an element which is which has Frobenius norm bounded by √2r, spectral norm bounded by 1/2. We add an I to it, and we need to make sure that this is PSD. Rescale it by lambda over 2. So the one thing I want to note is that, in fact, k of r is a subset of theta. So we're trying to find a subset of our parameter space, so we better actually have a subset of it. Remember that theta had every matrix inside of it was supposed to be with spectral norm bounded by lambda. So this better be the case here. And you can check that, well, you're taking a matrix, you're taking a matrix with spectral norm bounded by 1/2. So what you get is something with spectral norm bounded by 3/4. Sorry, by 3/2 by the triangle inequality. And altogether we have 3 times lambda over 4. So since spectral norm of any sigma in the set is bounded by lambda over 2 times 3/2 equals 3 lambda over 4 is less than lambda for sigma in case k of r. Okay, and so we will take, and of course this comes out of the technical arguments later, but I'll just tell you what works. So we'll take r equals 1 over n times p plus 1 over 2. Okay, so one can show that for sigma 1 and sigma 2 in k of r, write that again, in k of r, we have dkl of p sigma 1, oops, let's screen sharing just stopped again. Oh, no, I think I hit something. Okay. Yeah, there we go. Okay, we're back. So one can show that for sigma 1, sigma 2, and KR, we have pairwise KL divergences bounded. So this guy is less than or equal to 16R. And I guess this comes from the fact that it's one of these two things, that the Frobenius norm and the L2 norm of the matrices are bounded appropriately. So this gives us, and I'm not going to prove this, but this gives us the upper bound on pairwise KL divergences. So next, we show the existence of a large set, P1 up to Pm, which is a subset of K of R, which is two delta separated in spectral norm using a metric entropy / volumetric argument. Okay, so maybe one thing to note is that what I've set up here is that actually any two, if I choose any two parameters in this set, then the pairwise KL divergences are bounded. So in the previous construction, I first found a two delta separated set, and then I said that for these two delta separated guys, the pairwise KL divergences were bounded. This is saying that for any points that I choose, the pairwise KL divergences are bounded. Therefore, I can just focus on finding a separated set. Okay, and here again, I'm not going to say too many details. So, so here's a fact, or here are a few facts. So the two delta packing number is lower bounded by the two delta covering number. And just to say a word about this, well, the two delta packing number is the, so this is the max number of two delta points we can pack in, meaning that all pairs are two delta separated. The two delta covering number is the minimum number of points so that two delta balls around the points cover the set. Okay, so it's a standard result that the two delta packing number is lower bounded by the two delta covering number. And importantly, this is in turn lower bounded by the volume ratio. So volume of K of R divided by the volume of the set, which is B2 of 2 delta intersect SP. Okay, so essentially this denominator here is just asking me, well, what is the volume of, if I want to make sure that, so this is relating the two delta covering number to the volumes. So two delta covering tells me how many points are covered by a ball of radius 2 delta, right? So what I'm doing down here is I'm looking at the ball of radius 2 delta in the 2 norm, because I'm calculating everything in the 2 norm. I intersect with the PSD matrices, because that's really all I care about, and I take the total volume and I divide it by this volume. Okay, and then through a somewhat technical argument, so using some results in convex geometry, one can show that the latter quantity is lower bounded by some constant times lambda over delta square root of p over n to the power p times p plus 1 over 2. Okay, so I'm skipping the details because there are quite a lot of them. So if we accept all of this, what have we seen? Well, we've seen that we have a bound on the total number of points in the set. So this is going to be our capital M. And we have a bound on the KL divergences, which gives us a bound on I. And now we can just put it all together and plug it into Fano's inequality. So plugging into Fano's inequality gives a lower bound of the order, let's say constant. So this is just so I can be a little bit loose. Well, there was the phi of delta part, right? And phi here is the squared function. So I have a delta squared. Now I have 1 minus. I need to write down what I saw from the upper bound on KL divergences. So this is the 16R. Here R is equal to this quantity, so roughly p squared over n. I also have to remember to multiply everything by n since it's an n-fold product. So I have n times 16 p squared over n. And then there's a 1, but I'm gonna, well, it's not really important. And then I take the log of the number of guys in my set. So that's of the order of p squared log of c delta over c lambda over delta square root of p over n. And maybe just to disambiguate, let's make that a c prime. Okay, so the game, even though this is kind of ugly, the game, of course, is to lower bound this quantity here by 1/2. So we can try to see, well, the n's cancel out, right? And actually the p squareds roughly cancel out if I ignore the 1, and the p squareds cancel out. So really I should just be making this guy order of a constant. So what that means is that we can take delta to be order of lambda times square root of p over n. Okay, and this implies that well, let me not rewrite this. So this implies that the minimax risk is omega of, so then this delta gets plugged into delta squared, and I get lambda squared p over n, and that's what we wanted. Okay, last example, and I think I do actually have enough time for all of this. So what did we learn? Actually, maybe we should say something about this. Well, what did we learn is that in this case, as I said, we constructed a set so that all of the pairwise KL divergences were bounded, and therefore we just had to calculate the size of a 2 delta separated set. And although it was somewhat complicated, we were able to go through a volume argument, right, which leads to the final result. Okay, so let's see one more example. So this one is high dimensional regression. Oh, I should give a source for this. So as I said, most of the content from this lecture comes from Wainwright's book, but for this particular example that I just did on covariance estimation, the paper is by Zhongming Ma and Yihong Wu from 2015, and it's called volume ratio, what is it? Volume ratio, sparsity, and minimaxity under unitarily invariant norms. Okay, and as I said, all the examples that are in this lecture are going to show up later. And in the next lecture, I'll be using this lower bound for covariance estimation, which is why I wanted to derive it here. All right, so last example is high dimensional regression. And this is something we'll see in the 4th lecture when we start putting in computation constraints. So consider the linear model y equals x theta plus w, where w is IID noise, 0 sigma squared I, and x is fixed. Okay, and the goal is to estimate theta, which is in RP, where the true theta is k-sparse. So maybe let me just say, so well, we're looking at a case where, so y here is represents a vector, x is a matrix, and theta is the unknown parameter vector. And then we have another vector, an n-dimensional w. So you can think about w, maybe I'll denote this subscript in. This is IID noise. And here we're assuming we have a fixed design. So here we assume that x is fixed. So the only randomness comes from these draws of w. And we'll be interested in a high dimensional case. So the dimensionality of x is n by p. You can think about these as the IID observations. This is like x1 transpose up to xn transpose. And we want to recover theta after we observe y and x. So in this case, so we're thinking about p as being much larger than n. Okay, so our parameter space is going to be the sparse ball K. So really this means all vectors in R to the P with less than or equal to K non-zero coordinates. Okay. So we will show that infimum over theta hat, supremum over theta in theta of 1 over n times expectation of x. Oh, I forgot to say one more thing, so I will use my little lasso tool. Haha, that's ironic. All right, so we're going to look at this guy, and we're going to show that this is kappa L squared over kappa U squared times sigma squared K log. Okay, I get to use my lasso tool twice. Oops. You can see I don't use the iPad very often, huh? I'm going to move this guy down here. So we'll show that this is true. And I forgot to tell you what kappa L and kappa U are. So one more constraint. So we will assume that x satisfies kappa L of theta 2 norm is bounded by 1 over root n. X theta 2 norm is bounded by kappa U theta 2 norm for all sparse vectors. Okay, so this is a sparse eigenvalue condition. Okay, so just to reiterate, our parameter space of theta is just the k-sparse vectors, but we have a fixed design x, and we assume that our fixed design matrix has these upper and lower eigenvalues that are bounded. We are going to show this lower bound on the on what's called the mean squared prediction risk. Mean squared prediction risk. So you might ask, why am I not looking at just theta hat minus theta? And you could look at theta hat minus theta. In fact, if you have these nice conditioning bounds on the matrix X, then you can very easily change this guy to theta hat minus theta. The reason why I'm going to write it in this way is that, as I sort of alluded to, I will be returning to this example in the very end, in the last lecture, where I'm interested in computational constraints. And there it will be very important. Well, there I'm going to start to relax this lower bound condition in particular on the conditioning of X. Okay, and one can only do that in the case when we're looking at prediction error rather than theta hat minus theta alone. Okay, so oh yeah, one other thing to note is that theta hat here is usually a function of X alone, but this is a function now of X and Y. Well, X is fixed, Y is the guy who's random. Okay, so we will use Fano's method with L of UV is equal to, oops, this should be rho. Rho of UV is equal to 1 over root n times x u minus v 2 norm, and v of t is equal to t squared. Okay, so here's where I'm going to invoke a result. So using results from coding theory, there exists a subset, script V, which is a subset of -1, 0, +1, intersect B sub 0 of K, which is a subset of theta, such that the size of this guy is at least P minus K over K to the K over 2. And the Hamming distance between any two vectors is at least K over 2 for V not equal to V prime. Okay, so what I'm going to do is I need to create this 2 delta separated set, right? And just as in the mean estimation case, I can create some arbitrary set and then rescale it by a factor that involves delta to make it 2 delta separated. So this result from coding theory says that if I just use binary values, or really ternary, -1, 0, and 1, and I'm only allowed to have sparse codes that have K values, then I can find a well-separated subset of codes. And this sort of result comes from coding theory, from error correcting codes, when you want the codes to be far enough away in Hamming distance so that having some errors will still allow you to tell what the original code was. So in particular, for V not equal to V prime, I have V minus V prime in 2 norm is going to be at least square root of K over 2. Right? And this comes from the fact that all of the values are -1, 0, or 1. So if the Hamming distance is at least K over 2, then every component is at least, well, I have at least K over 2 components, which are different by at least 1 each. Okay, so now we rescale. We take theta V equals to 2 delta over kappa L times square root of 2 over delta times V. Then we can check that we have a 2 delta separated set. So we have to look at our row metric, which was x times theta V minus x times theta V prime. Okay, so our conditioning assumption implies that this is lower bounded by kappa L times theta V minus theta V prime. And this is in turn lower bounded by kappa L times, well, I have my rescaling, 2 delta over kappa L times root 2 over delta. I don't know why there's a bracket here. Let's get rid of that. And then the separation here was square root of K over 2. Okay, so that comes from this guy, goes over there. Okay, so if I chose everything correctly, oops, sorry, that's not a, sorry, yes, there's a misprint here. There should be a K. So they want this K to go away. And altogether this is 2 delta. Good, so everything is 2 delta separated. And then the other thing I need to do is check that there's an upper bound on the pairwise KL distances. So also the pairwise KL distances are equal to 1 over 2 sigma squared x theta V minus x theta V prime 2 norm squared. So this equality comes from the fact that I have normal distributions. Remember, y is the only random thing, and we're conditioning on the value of, in this case, x theta V and x theta V prime. So you can use the formula for KL divergence between Gaussians that I gave earlier in the lecture. And this is in turn bounded by, well, I can get rid of the x's using my conditioning assumption. So I have n kappa u squared over 2 delta squared times theta V minus theta V prime 2 norm squared. And I believe we can check that this is 8 delta squared over kappa L squared K times 2K. Why is that? Well, let's assume that I did everything correctly, but at some level there's the square of this guy is in here. And then I think this comes from the fact that everything is K sparse. Yes, okay, so this is just the square of this guy right here. And then everything is K sparse, so there are at most 2 K places in which they separate. Okay, and so this is my upper bound on pairwise KL divergences. So then Fano's inequality gives the lower bound Okay, so I have my delta. I square it because phi was the squared function. I have 1 minus my upper bound on the KL divergences, which here should be 8 times n delta squared over sigma squared times kappa u squared over kappa L squared plus 1. And then the size of the set here was, there's the size of the set. Right, the size of the set is this, so the log of that is order of kappa k over 2 times log base 2 of p minus k over k. And now I again play this game where I want to bound this by 1/2. And one can check that the right choice of delta should be that delta is order of kappa, delta squared is order of kappa L squared over kappa U squared times sigma squared k log of p minus k over n. Okay. And this is the rate that we had up above, and the bound is achievable using the lasso estimator. And let me not state it right now, because we're going to state it again in the 4th lecture. Okay, so I think I'll stop there. One last thing that I'll mention is that I think as advertised in the abstract of this talk, I said I would talk about Fano's method and 2 other methods, Lecam's method and Aswad's lemma. I decided not to talk about these and just to focus on Fano throughout this tutorial. But there's a nice paper by Bin Yu from 1997 that's called, I don't remember what order it is, but let's say Lecam, Aswad, and Fano. That's worth a read. And it gives examples of when you might use the other bounds to prove, the other lemmas to prove lower bounds as well. Okay, so I'm happy to take some questions and then maybe go into the break.
Okay, thanks very much, Po-Ling. And any questions from the audience?
Just a clarification question. If the restricted eigenvalue condition, that's by itself, isn't that an implication of sparsity if there is a randomness in the design of X?
I'm sorry, what were you asking? What the randomness of the design next?
So the restricted eigenvalue condition you stated as an assumption, but isn't that also an implication under the randomness of X?
Yes, that's true. Okay, so in this case, for these bounds, we're assuming that X satisfies these bounds, but this will hold with high probability if you generate the rows of X IID from some, let's say, sub-Gaussian distribution that's well conditioned.
But yeah, I just want to double check that. Thanks.
Yeah.
More questions?
Hi, Po-Ling, this is Anru. Very nice tutorial. So I have a question. So if the KL divergence between 2 distributions happens to be infinity, and do you have any other, say, measure metrics other than the KL divergence to replace?
Yes, I think. Well, I don't know of examples off the top of my head, but I do know that for Lecam's method, for instance, it's in total variation distance. So that could be a possibility for a case in which you might use Lecam's method instead.
I see. So one example I can think of is that if these 2 distributions have separate supports, then the KL divergence will be just infinity.
Right. Yeah. So in that case, you would not want to use these Fano's methods. Yeah.
Yeah. Thank you.
Anyone? More questions?
Actually, this was a question like in response to the previous question. If you actually have 2 distributions with disjoint supports, like this is the law of your data, doesn't that mean you can perfectly distinguish the 2 parameters from the data?
Oh, Yeah, I guess that would be true, at least for Anru's specific question.
In the sense that there is one point which makes it infinity, but it's a small probability set.
Yeah, that's right. That's right.
Then you can still use the TV distance. Yeah, TV is actually the first principle of statistics. And you put a single KL divergence as a relaxation of the TV distance. It's actually some form of upper bound of the TV distance. Yeah, and so if KL fails, then you go back to the first principle and see whether TV works.
Mhm. Right, but mutual information, I mean, if you're going to use Fano's method, then you want to bound on the mutual information, which I think would already be infinity. But yeah, I mean, like all of these come from hypothesis testing problems. So you could use TV distance instead of KL divergence in order to characterize the probability of error, which I guess is what happens in the case of using Lecombe's method instead.
Okay, great. So I guess let's wrap the questions for now, and then Po-Ling, if it's okay with you, maybe we'll take a 20-minute break instead of the advertised 15-minute break, just to give people a little bit more time to digest the first half.
Okay, sure.
Okay, great. So let's wrap up, and then we'll be back in 20 minutes. 11. Thanks so much.